Hello Year 11s and welcome to the next video installment. Guys, today we're just going to be doing a very quick summary of redox reactions and a summary of electrolysis so that we are all up to speed for this week's focus, which is the industrial application of electrolysis. And hopefully it will be nice for you guys to see that some of these things actually do have some real life applications. So guys, just a very quick summary of our redox reactions. We already know that redox stands for reduction and oxidation. And by reduction we mean a gain of electrons. And oxidation we mean a loss of electrons. So we've all been aware of the shorthand way of remembering that, which is oil rig. An acronym, I think, is the correct English term for that. Guys, reduction involves a decrease in oxidation number. And it's fair to say that it is our non-metals, so as atoms, our non-metal atoms undergo reduction very readily. They are very keen to gain electrons in order to have a full outer shell. And our oxidation reactions, or things that are oxidized, will increase in oxidation number. And it's fair to say that our metal atoms regularly and readily undergo oxidation. Guys, a reduction half equation would look something like this. Let's take bromine, for example, a reasonably reactive halogen. And if we add 2 electrons to bromine, then we form 2 bromide ions. And hopefully you guys can see this bit: gain of electrons, gain of electrons. And take a metal atom, for example magnesium, readily gives up 2 of its electrons to form the magnesium ion and 2 electrons. So they should be concepts that you guys are more than familiar with. Now, if we were talking about normal redox reactions, then they usually occur spontaneously, which means that you don't have to put any kind of external energy into them, okay? They just happen readily. Guys, as we've been looking the last couple of lessons at electrolysis, one thing to note about electrolysis is that it is non-spontaneous. So what I mean by that is you have to inject some type of energy into it, and that comes in the form of, it might be a battery or electricity, in which case you would be using a power pack. And what the objective of electrolysis is to convert or use this electrical energy to drive chemical change that would not otherwise occur. So the whole idea is that they're non-spontaneous, they don't happen by just sitting around, but if you give them enough electrical energy coming from a battery or a power pack, then you can use that to drive chemical change. So, for example, if you were to take molten, let's say copper chloride, copper 2 chloride to be more specific, and I'll just draw up a beaker. So guys, by molten copper chloride, I mean it's in its liquid state, so essentially it's been melted. So this beaker is full of molten copper chloride. Now guys, in actual fact, because it's no longer in its lattice form, these ions are now free. So we can draw some in like this. Now in this electrolytic cell, you will have what is called, that is a very, very ugly looking electrode. Let's try that again. That's better. So, guys, we have an electrode at one side and an electrode at the other. Now, all these electrodes they're inert sites, if you like, for a chemical reaction to take place. So in this example, we would be using, let's say, a carbon electrode, like a graphite electrode, because it's inert enough for our purposes. And you need to be injecting some type of electrical energy into this cell, so we will have a battery. And this battery will be in the middle of an external circuit between our two electrodes. Now, for argument's sake, I'm going to say that on the left-hand side we have the anode, and on the right-hand side we have the cathode. Now, guys, it's important to understand a couple of key things about both the anode and the cathode. So at the anode, oxidation occurs. Therefore, by default, at the cathode, we have reduction. And you can remember that by using the sort of helpful tool of red cat. Now, guys, the objective of this battery is to essentially suck electrons out of the anode and push them into the cathode. And because the anode is where oxidation occurs, it's where the loss of electrons is. So it's very easy for the battery to suck the electrons from the anode, or the site of where electrons are produced, and it pushes these electrons into the cathode. So this cathode is the site of reduction, or the gain of electrons. If the anode is the site of oxidation and where these electrons are lost, then it itself has a positive charge, because it is losing electrons, it's losing a negative charge. So the more electrons it's losing, the more positive it's becoming. And likewise, but opposite, the cathode is gaining electrons, so it's gaining a negative charge, and it becomes, therefore, negatively charged. Next step is to understand that if the anode is establishing a positive charge, then it starts to attract negatively charged ions. So the chloride ions start to migrate towards the anode. So anions, because remember that's the name for a negative ion, anions are attracted to the anode, A and A. And in similar situation, if your cathode is establishing a negative charge, then it starts to attract the copper, or the cations. And once your charges are established and you start attracting your respective ions, then reactions take place. So if you are attracting a negatively charged ion, and in this case it's the chloride ion, to the anode, then it follows. This is what happens. Because that is the reaction for the oxidation of the chloride ions. And similarly, the copper is attracted to the cathode and undergoes reduction. So it gains 2 electrons to form the copper metal, and it's going to be solid. And what then happens, guys, is you can tie in some observations to this electrolytical cell. So for example, if you're forming Cl2, that is a gas, and it is a green gas. It's a very pale green, pale yellow gas. So that actually starts being produced and comes off the anode. So you can actually see a yellow-green gas being emitted, and likewise you can see a salmon pink metal of copper starting to coat your cathode. So it's a way of kind of getting solid, very valuable, useful copper from a molten copper salt. Hopefully, guys, this actually explains to you why in a normal school lab it's actually quite dangerous to run electricity through aqueous or molten sodium chloride, because it produces chlorine gas, and that is very toxic. So guys, the next installment we will cover is the industrial application of this, but hopefully you guys can see that there is actually some benefit to being able to get our sort of purified elements of copper and chlorine from our impure molten copper chloride salt. Until next time, happy study.